Congratulations on hitting the end of this chapter where we were learning about polymorphism. We started out by looking at what polymorphism really means. And polymorphism is really about using a base class pointer or reference to manage your derived objects that are part of the same inheritance hierarchy. We saw that one of the benefits of polymorphism was to be able to set up functions like this that take a base class pointer or a base class reference. And you can use these kinds of functions to handle any kind of derived object from the same inheritance hierarchy with the base class here at the top of the hierarchy. So for example, here we are taking a shape pointer and reference, but we can use these functions to draw rectangles, circles, triangles, or any kind of shape whose class is part of our inheritance hierarchy. We can do something like this. Another benefit was that we can use the base class pointer as a type to store these guys in a collection. For example, this array here is storing shape pointers, but we can pass in addresses for circles, ovals, rectangles, or any kind of crazy shapes we have with our shape inheritance hierarchy, and this is going to work. If we loop through this array, we could get the draw methods to be called using dynamic binding, and this was really cool. We started the chapter by looking at the fact that we don't get dynamic binding by default in C++. What we have by default is static binding, and what that means, the C++ compiler is just going to look at the type of the pointer to decide which method to call from your inheritance hierarchy. So from here, we would wish for the draw method to be called for a shape, and that's what we're going to see. But if the shape pointer is managing an oval object, we want to call the draw method from oval. We will be calling the draw method from shape here. And this is static binding. The compiler is going to just look at the type of the pointer. It's not going to look at the type of the object that the pointer is actually managing. And this is static binding. We will get static binding by default if we use a base class pointer to manage a derived object, like we do here. But we will also get static binding by default if we use a base class reference to manage a derived object. And we have a bunch of examples of this here. This is going to do static binding by default, and our methods are going to be called at the shape level. And that might not be what we want. If we want to get dynamic binding or polymorphism, all we need to do is really simple, is to mark our draw methods as virtual. If we do that, this is going to opt our classes into polymorphism. And if we happen to call the draw method on a base class pointer, we're going to call that method on the most specialized object we have in our C++. So if our base class pointer or reference is managing an oval object, we will call the draw method at the level of oval. If we are managing a circle, we will call this method, and this is going to be really cool. We moved on and looked at the fact that polymorphism is not free. If we set up polymorphism with the virtual functions, our objects are going to be larger. And we saw that if we assign a derived object to a base object like we are doing here, we are going to get a phenomenon called slicing. In other words, derived parts of our object are going to be sliced off, and we are going to be left with the most base part of our class, and we are going to assign that to our object here, and our data is basically going to be sliced off. You need to be aware of this. We moved on and saw that if we store direct polymorphic objects in a base collection like we are doing here, we have an array storing shape data, and we happen to put in a circle, oval, or any kind of crazy objects we have in our inheritance hierarchy. One thing is that this is going to compile, but it is going to slice off derived class information. So if we loop and call the draw method, we will be calling the draw method from shape because circle and oval information has been sliced off the moment we try to store these objects in a collection that is designed to store shapes as we have here. So this is something you need to be aware of. If you want to keep derived information, you should use base class pointers, and that's going to keep your information. Your draw methods here are going to be called polymorphically. One thing you should know is that we can't store reference in a collection, and the reason is that they are not left assignable, and we had a chance to look at that in the chapter. We moved on and looked at the override specifier, and this is something you can use to make your code much safer, in that you make sure that you are overriding a method that really exists in your inheritance hierarchy from the top class. If the method doesn't exist, you're going to get a compiler error. We also had a chance to explore the concepts of overloading, overriding, and hiding. We saw that we could set up overloaded virtual functions, and here is a simple example. We have a draw method that takes one parameter, and we have a draw method which doesn't take a parameter. If we go in our derived classes and set up a single override of our function overloads, this is going to hide all the other overloads we had. And if we want them to be available, we need to explicitly override them in our derived class here. Another thing is that if you go down in your inheritance hierarchy and set up another overload, this is not going to be recognized in shape polymorphism because we don't have this method at the shape level in our inheritance hierarchy, and we had a chance to play with this, and you need to really be aware of this. We moved on and saw that we could do polymorphism at different levels. For example, we can do animal polymorphism, we can do feline polymorphism, we can also do bird polymorphism. You really need to decide where you want to do your polymorphism depending on the design that you are after in your C++ application. We saw that we could do polymorphism with static members in our classes, and we saw that it is possible to set up static members at different levels in our inheritance hierarchy. We saw that we could use the final keywords to restrict how people override methods in derived classes, or restrict how you can derive from base classes. This is something you can do if it makes sense for your C++ application. We saw that final and override are not real C++ keywords. We saw that we could do something as crazy as this, but just because you can do this doesn't mean you should, because it is really going to make your code confusing, so don't do this. We also had a chance to look at how access specifiers work with our virtual functions, and we saw that if we use polymorphism, the access specifier we have in the base class is going to matter. The access specifier we have in our derived class won't really make a difference with polymorphism. So for example, if our virtual function is public in the base class, it would be accessible through polymorphism, even if what we have in the derived class is private as we have here. If we happen to make our virtual function in the base class private, we won't be able to access it through polymorphism, and this is not going to be much useful in your C++ code. You need to be aware of this. We saw the behavior we experience if we use virtual functions with default arguments. We saw that by design, C++ compilers are going to plug in default arguments statically. So this is really going to be confusing if you expect this to also be part of polymorphism. We learned about virtual destructors, and the syntax to do that is really simple. You just use the virtual keyword with your destructor, and this is going to make sure your destructors are called in the expected order and release your memory as you expect. If you don't do this, you're going to get a bunch of undefined behaviors in your C++ programs. We saw that we could do dynamic casts to turn our base class pointer into a more specific object that we can call non-polymorphic functions on. You can do this if it makes sense for your application, but don't overdo this, because if you do this a lot, that's possibly a sign that you are doing bad design in your C++ program. If you need to call this function a lot, so why not make it virtual in the first place? This is my argument here. We saw that it is really bad to call virtual functions either in constructors or destructors, because that's not going to really use polymorphism. If you want polymorphic behavior, you can call your virtual method explicitly after your object is properly constructed or before you release the memory. That's going to give you polymorphic behavior, and this is what I recommend to use in your C++ projects. We had a chance to learn about the type ID operator, and we saw that this was a way we have in C++ to ask our base class pointer or references which kind of dynamic object they are managing. So they are going to tell us, and we're going to see this information, for example, if we print this out with stdc out statements like we are doing here. We had a chance to learn about pure virtual functions and abstract classes. The syntax to make a function pure virtual is what we have here. And at the moment you set up a single pure virtual function in your class, the class is going to become abstract and you lose the ability to create objects of that class. This is what we had a chance to learn about here. Once you mark a function as pure virtual, you won't have to put in an implementation for it in the base class. The implementations are going to show up in deriving classes. Any derived class is going to be forced to override all these pure virtual functions. If it leaves even one, it is also going to become abstract, and it won't be of much use in your C++ program. So if you derive from an abstract class, make sure to override all the pure virtual functions to be able to use your derived class like you would want it to be used. We closed the chapter by looking at abstract classes as interfaces, and we saw that an interface was a class with only pure virtual functions and no member variables set up in that class. And we saw that we could really do all kinds of crazy things with interfaces. For example, we could attach our interface to our classes to attach more powers to our classes without having to set up those things in our classes, and that was really cool. We were able to set up an output stream operator for our classes without having to do that explicitly in our class, and that was really powerful. This is really all I had to share in this chapter. I hope you found it interesting. We are going to stop here with this one. In the next one, we're going to learn about exceptions in C++. Go ahead and finish up here and meet me there.